In this video, we learn about the connection of the reaction Gibbs energy and chemical equilibrium. Alright, let's think about a very simple reaction such as A turning into B, and these might be solutes in a solution, right? So this might be maybe a reaction inside your body. For example, the second step in glycolysis is the isomerization of glucose 6-phosphate into fructose 6-phosphate, right? So that is just one molecule turning into another at low concentrations inside your cells, right? So we could actually try to use that for this example. Now, the point of this video is to introduce the concept of chemical equilibrium, which is pervasive in chemistry. All right, so let's think a little bit about that reaction. What I'm going to do here is plot how those concentrations of A and B change on time. Right, so that is going to be the molar concentration, and I'm going to plot both A and B and see how they change in time. So let me actually use two different colors for that. Blue is going to be the concentration of A. So this is our reagent, and we're going to start the reaction with quite a hefty concentration of A. So we may have something like this, and then red is going to be B, which is the product, and we're going to start the reaction without any product, so that would be right here. Okay, so as the reaction starts, then the concentration of A will fall down, and the concentration of B will grow up commensurately, right? Notice that the stoichiometric coefficients are 1 to 1, so there you have it. That will be a transformation of A into B. So what you will actually see is that those concentrations may look like that. Okay, and the concentration of A of B is going to look like this, my product. All right, so this is B, and this is the concentration of A. Okay. So something interesting happens here. If you let this reaction run essentially until infinity, there's always going to come a point in which you no longer make progress from reagents to products, right? There comes a point, which is perhaps right around here, in which you can clearly see that the concentrations of reagents on products don't change anymore, right? So that's the point where you actually reach equilibrium. So from here onwards, you have equilibrium. And notice that something happens here, and that is that those concentrations don't change, and actually those concentrations then are dictated by something that we call the equilibrium constant, and that is simply the ratio of the concentration of B over 1 molar over the concentration of A over 1 molar, right? So that is your equilibrium constant that you guys have learned how to write in general chemistry, analytical chemistry, and almost any chemical course that you've taken, okay? But prior to that, you actually do not have a situation of equilibrium. So this actually is something that is quite useful in getting a little bit of a deeper understanding of what the reaction quotient is. Notice that if we were to write the reaction quotient for this expression, right, it is that, well, that is simply going to be the activity of B over the activity of A, but of course these are solutes, so that is the concentration of B over 1 molar, or the concentration of A over 1 molar, right? And then you will say, well, isn't this then the same thing as the equilibrium constant? And the answer is not quite. Notice that this reaction quotient can be written at any time during the reaction, right? So if you're right here, you're not at equilibrium, but you can still write what the reaction quotient is going to be. That is simply the concentration of B over 1 molar over the concentration of A over 1 molar. All right, and it so happens that after you reach equilibrium, then the reaction quotient is identical to the equilibrium constant. Okay, so as a matter of fact, if you want to do this correctly, right, the separation between the reaction quotient and the equilibrium constant is that the reaction quotient works always, right, even if you're not at equilibrium, but the equilibrium constant only works once you have reached equilibrium. Okay, so in other words, the reaction quotient is a more general expression than the equilibrium constant, because the equilibrium constant only works once you have reached equilibrium. Okay, so again, they're the same, reaction quotient, equilibrium constant. Only when you're at equilibrium, you can use the reaction quotient elsewhere. Okay, great. So the question then now is, well, thermodynamically, how would we then envision chemical equilibrium? Is there a way that you can use some knowledge of the reaction Gibbs energy to predict where that equilibrium is going to be? And the answer is yes. As a matter of fact, we can do that relatively straightforward. Notice that this is our general expression to predict whether a reaction will be spontaneous or not, right? So our goal here is to try to see how this looks like once you reach equilibrium. Okay, so, well, this is actually much easier than it looks, right? At equilibrium, what happens is that the reaction is neither spontaneous left to right or right to left. Instead, you're at equilibrium, right? So the value of this is 0. That is the condition for equilibrium. And then what also happens is that once you reach equilibrium, this reaction quotient actually reaches a value that we call the equilibrium constant. So those are the two changes to this expression to equilibrium, right? That value is 0, and then this value is just the equilibrium constant. So our expression simply turns into this. 0 is going to be equal to delta RGM, the standard state, plus RT, natural log of K. All right, but we can actually then solve this in a couple of different ways, which I'm going to write right here. The reaction Gibbs energy, the standard state, is equal to minus RT, natural log of K, or K is equal to e to the minus delta RGM, the standard state, over RT. Okay, there's a lot of power in these expressions. As a matter of fact, some books tell you that this is actually the most powerful or most important expression in thermodynamics for chemical applications. In my view, personally, I think that this is far more powerful, right? Because it contains the situation of equilibrium, which is this one, but it also allows you to calculate spontaneity of chemical reactions even if you're not at equilibrium, right? Even if you're setting up your reaction under some concentrations that might be of interest to you, right? So this is just a special case of that expression, which to me is the most important in all of a chemical course in thermodynamics, okay? Let's actually try to then review why this is so important. These equilibrium constants can be used in problems that you learn how to work in Gen Chem and analytical chemistry. This will be the problem of maybe having a weak acid and predicting what the pH of that solution is going to be, or maybe having a sparingly soluble salt and determining what the concentrations of those ions are in solution. All that comes from here, that knowledge of those equilibrium constants. But what we learn here is that those pK sub A's, K sub SP's, and all of those values of those equilibrium constants are actually connected to the reaction Gibbs energy at the standard state. And this is key because, of course, calculations of the standard state are straightforward. You just got to go to tables and get either the values of the Gibbs energies of formation or maybe the enthalpies and the entropies, right? So this we know how to calculate. What this is telling you is that you can get something as powerful as the value for an acid constant or a base constant or a solidity product or any equilibrium constant simply from those values that you can get from thermochemical tables, right? So the power of that is amazing, right? So this is kind of the culmination of a semester in thermodynamics in the chemical sciences, right? The idea that building from the first law to the second law, we can get to something that is the reaction Gibbs energy, or the Gibbs energy in general, and that is just a condition for spontaneity and equilibrium that can be used under constant pressure and constant temperature, right? So that Gibbs energy controls really the stability, spontaneity, equilibrium of pure substances, but also of chemical reactions. Ultimately, this reaction Gibbs energy at the standard state is actually connected to the equilibrium constant of a chemical reaction, which again is something that allows you to learn things as important as what is the pH of a solution, or what are the concentration of ions from a solution of a sparingly soluble salt.